Hi, and welcome to this educational video brought to you by the Society of Mechanical Ventilation. Mechanical Power.
Hello everyone. Today we'll talk about a little bit complicated topic. Try to make it simple, which is the topic of mechanical power. We'll talk what's the definition of energy and work and power. How do we calculate the mechanical power? What's the relation of this mechanical power to ventilator-induced lung injury? We'll talk also about trans-pulmonary mechanical power and some problems with mechanical power and issues to think about in the future. Quickly, we'll talk about the evolution of lung protective ventilation through the years. And this line, I like this slide, it goes from 1974 till nowadays, excuse me. We don't have to go through it all, but it's go through that when did we start to understand volutrauma, barotrauma, PEEP, the baby lung concept, the open lung approach back in the early 90s. Then came the low tidal volume ventilation. As you can see, 8 years later, transpulmonary pressure. Then 5 years later, stress and strain concept, followed by the driving pressure. 2016 came the mechanical power topic described by Gattinoni and Marini, which we'll be talking about. And after that, followed by 2018, the closed loop ventilation. So as you can see, we are progressing, I think pretty slow, but there's more to understand. I don't think we're at we fully understand lung protective ventilation as of yet. Before we talk about mechanical power and energy, we have to first touch base on the equation of motion. We all know the equation of motion, which describes the pressure or the work basically taken to move the tidal volume to the lungs. So the ventilation pressure has to overcome the elastic pressure, which is to inflate both the lungs and the chest wall. So the elastance of the whole respiratory system, as we know, divided into chest wall and lungs. Also, it has to overcome the resistive pressure, which makes the air flow through the airways, and has to overcome also the PEEP. And by PEEP is the total PEEP to keep the alveoli open. So if we put this equation, it will be the P mus and the P vent. We always, sometimes, not always, forget that there is a patient there and his work has to be considered. If the patient is passive or paralyzed, so of course the ventilator is doing all the work, the P vent. Most of our patients are not paralyzed, so we have to add the P muscle, the muscle pressure, plus the P vent because they work together, and it has to overcome the P elastance and the P resistance, and again the total PEEP. Total PEEP meaning the dialed PEEP plus the auto PEEP. So again, if you put the equation here, it will be to convert everything into pressure. The P mus and plus the P vent will be elastance times volume, because we know elastance is pressure over volume, plus we have the resistance times flow, and again we know resistance is pressure over flow. So all of this to convert to pressure, plus the PEEP total, as we talked about. And that equation of motion describes basically all the effort or the work need to move the air, and the mechanical power will be all derived from here. So what is the mechanical power? Mechanical power basically depicts the energy transferred to the respiratory system by the ventilator, and again the ventilator and the patient during a certain period in time. So it's joules per minute. So we know from Newton's law that work, which is only in joules, equal force. So there is a force by the ventilator and the patient, that's a pressure, that causes displacement or movement of tidal volume. So it's basically pressure times volume, that's work in joules. But when we convert to power, Now that's joules per minute. Now we have to add a conversion factor to convert this into joules per minute, and we have to do the respiratory rate. So it becomes that conversion factor times respiratory rate times pressure times the volume.
So, mechanical power and the components of the mechanical power. This is from a lecture by Dr. Gattinoni, and the components of mechanical power basically every setting we set on the ventilator, from pressure, volume, flow, respiratory rate, and PEEP. And this all supposed to contribute to barotrauma, volutrauma, atelectotrauma, and biotrauma. So for years and years, and we knew that the pressure and the volume contribute to ventilator-induced lung injury, and there was always the debate of which one is more injurious to the lung. But we really never thought much about the flow or the respiratory rate or even the PEEP, although we know that the PEEP with the atelectotrauma can contribute. But if you remember the ARDS network, because of the low tidal volume and the patient becomes hypercapnic, so what happens is most clinicians have to increase the respiratory rate. And by increasing the respiratory rate, actually it contributes a lot to mechanical power. So we have to pay attention basically to every setting we do on the ventilator, because they can all contribute to injury. This is another slide also from lecture by Dr. Gattinoni, and describes the mechanical power. As we said, mechanical power is basically pressure times volume and the respiratory rate. And this was the initial equation kind of that he describes in 2016, which a little bit complicated, but basically 0.098 is the conversion factor times the respiratory rate times a change of volume square plus half the elastance of the respiratory system, that ERS, plus the respiratory rate, and that part describes the work or the pressure to distend along. So that's the elastic part. Multiplied by the 1 plus the I to E ratio over 60, multiplied by the I to E ratio times the resistance, and that describes the resistive part of the work or the power. Again, plus the change in tidal volume multiplied by the PEEP, and that describes the PEEP power. So as you can see here, it's described into three components. That part which distend along, the first one, that's the elastance or the elastic power, and the middle one is the resistive power, and the third one is the PEEP power. If you look at that other slide on the right side, and we'll come to this again later, but basically describe the resistive work is the work dissipated as heat in generating flow through the airway resistance. The elastic work is the work needed to expand the lung and the chest wall. And the PEEP work, which is the work against PEEP during inspiration, that's temporarily stored as energy within the elastic tissue. Again, I'm gonna skip these two other paragraphs here, and then we'll come to back them later. Here we'll talk about the components of the work, and if you see this figure on the left, this is the pressure volume curve in volume controlled mode with the constant or square waveform, and on the right side here, that's a pressure controlled mode with a decelerating waveform. As you can see, there's a difference in the shape of the pressure volume curve, and you can see the area under the curve and the pressure controlled on the right side is bigger. And we proved it in a bench study that unfortunately pressure controlled ventilation gives higher work or power compared to volume controlled mode with the square or the constant flow. But let's divide that curve here, go back to that left one on the volume control. And as you can see, the area in blue It's called the elastic power. So that's a part of the equation that related to the elastic component. And again, we divide this elastic part into two sides. The left side here you can see PEEP, so that's called the elastic static component. And on the right side we call it the tidal pressure, which is the elastic dynamic component. And in the green side, that's the resistive work. Let's go to the pressure control on the right side. Again, the blue area is the elastic component, and again to the left is the PEEP, which is the elastic static, and to the right is the tidal work, which is the elastic dynamic, and the green area is the resistance. So you can see again that the resistance in the pressure control, the resistive work, is actually bigger than the volume control. But versus the PEEP and the tidal, if you use equivalent tidal volume and driving pressure, it's usually the same. So let's go again and to that writing on the right that we were talking about in the last slide. So again, the resistive work, which is the area on the right in the green, that's a work dissipated as heat to generate flow through the airway resistance. The elastic work, which is the area on the left, the work needs to expand the lung and the chest wall, so both the whole respiratory system. The PEEP work, which is that elastic static part of the elastic component, that's a work against the PEEP during inspiration that's stored as energy within the elastic tissues. There's a newer concept called the inspiratory work, which is they ignore the PEEP, they remove the PEEP work from the equation, and because it's only a static component, and they keep, basically it will be the sum of the tidal work and the resistive work. The tidal work, as we said, which is that triangle, half of the elastic to the right, that's the elastic work minus the PEEP work. And of course, total work is the whole area under the pressure volume curve. And measuring the work with the pressure volume curve is probably a much accurate way in calculation than just the other formulas that we'll talk about. So now let's talk about calculating the mechanical power. And there is many equations. The first one by Gattinoni, the one that we showed before, which was like a little intense and complicated. So more equations came to simplify it a little bit. And of course, there's given that the pressure volume curve is different in volume control versus pressure control, so there was different equations for each mode. To simplify it, it's, if you look at the table, it's the change of volume multiplied by the change of pressure multiplied by the respiratory rate multiplied by the conversion factor to all get us to the mechanical power. Again, the tidal volume is here, the pressure, which is in the middle, again the elastic static component, which is usually the PEEP, the elastic dynamic component, which is the tidal work, and plus the resistive component. So in volume control mode, there's another simplified equation by Gattinoni, which is the first one, tidal volume multiplied by the peak pressure minus both the plateau pressure minus PEEP, which is basically the driving pressure, divided by 20, and multiplied by the respiratory rate, this to get us the power of inspiration, and then by the conversion factor to get us mechanical power. Another equation by Giosa, the change in tidal volume multiplied by the peak inspiratory pressure plus the PEEP plus the flow divided by 6, all divided by 20, and multiplied by, of course, the respiratory rate and the conversion factor. I think they made it 0.1 instead of 0.098. In pressure control, Bescher and colleagues did this equation, which is simplified a little bit, but it's the same concept. Change of volume, multiply by the PEEP, multiply the inspiratory pressure with 1 minus elastance with the power inspiratory time, multiplied by respiratory rate, multiplied by the conversion factor, which again they try to simplify it by only changing tidal volume, multiplied by PEEP, multiplied by inspiratory pressure. And there was another simplified equation also called the 4DPR, which I'll put it in the reference at the end of this. This is a practical exercise a little bit from Hamilton Medical as an example to calculate the mechanical power in the volume controlled mode and in the pressure controlled mode. The left one is in the volume controlled mode. The equation used is the expiratory minute volume multiplied by the peak pressure plus the PEEP plus the inspiratory flow divided by 6 over 20, the one that we talked about it in the other other slide. So in this example here, the expiratory minute ventilation is 5.8, which is basically the respiratory rate times tidal volume. The peak inspiratory pressure is 23, as you can see here. PEEP is 5. The inspiratory flow is 43 divided by 6, all divided by 20, which comes to mechanical power of 10.2 joules per minute. On the other right side here, this is in pressure controlled mode, as you can see it. The equation is 0.098 multiplied by the respiratory rate, which is 12 here, multiplied by the delta pressure, which is the driving pressure, plus the PEEP. So if you notice, so here's the equation 0.098 multiplied by 12 multiplied by the tidal volume. Here it's 498, so because of the equation it takes it as liter, so it becomes 0.498 multiplied by the inspiratory pressure will be 20, so the resultant mechanical power is 11.71. And I'll put also this reference at the end of the talk. We talked about this couple of slides before about calculating it according to a pressure volume curve, and I like this figure, and I'll put again the reference at the end. Again, on the left side here is in the volume controlled mode. To the left is the elastic power, which is again divided into PEEP or the static one and the tidal or the kinetic one, and the yellow one highlighted here is the resistance, and in the middle one is in the pressure controlled mode. Again, you can see the difference. The highlighted in blue is the elastic power, again two components, the PEEP, which is the static one, and the tidal one, which is the kinetic one. And highlighted in yellow is the resistive one. The interesting one is in the curve on the right side. That's a patient who's breathing spontaneously. So if you notice that the airway pressure at the bottom of the figure here, it's a sinusoidal waveform, and it's only composed of the elastic, which is the blue, as tidal work. There is no PEEP here because supposedly a spontaneously breathing person does not have PEEP or auto-PEEP, unless of course in obstructive airway disease. And the resistance, again, that looks like the sinusoidal. So again, just highlight the difference between assisted breathing on different mechanical ventilator modes and spontaneously breathing person with his own normal PMAS. The other two ones are passive patients. So for this slide, we'll use a simulator called the SIVA simulator, which is donated to us by Professor Robert Chadburn, and you can download it from our website, societymechanical-ventilation.org, under education, under simulators. So we'll see here, we're going to start with the volume controlled mode. Here the compliance is 0.04 liter per centimeter water, or 40 milliliter per centimeter water, which is elastance of 25 centimeter water per liter. The resistance here is 10. This is the effort model, or the patient effort, and we're here keeping the PMOS 0 as passive. Now you can change the setting, of course. This is the flow to control the inspiratory time and the I to E ratio, tidal volume, and if you look at here on the right side, the pressure volume curve, any changes, if we're increasing the tidal volume, you can see it goes up and the shape of the curve of course changes. Let's stick with the 400 for now. Respiratory rate 17, PEEP of 5, and let's put a little pause to see the plateau pressure, just a little bit. So it gives you the peak inspiratory pressure, total cycle time, I to E ratio, duty cycle, plateau pressure, driving pressure, mean inspiratory pressure, everything. And more importantly, here on the red, this is the passive. It gives you the ventilator elastic work and the ventilator resistive work, and if you add them together, it becomes the total work. And this is the ventilator work, which is the same. Patient work is 0 because we made him passive. So the total work is 0.53, and to convert it into power, the ventilator inspiratory power, as you can see here, it's 9.03 joules per minute. So let's see what the effect happens if we worsen the compliance. Again, this is volume control mode, so the tidal volume will remain the same, the pressure will change, the flow is the same, everything is the same. You can see the curve now shifted to the right, the blue area, because that's the tidal power of course got higher, but the resistive area is still the same. So let's change, look, and again the ventilator inspiratory power became 12.34. Let's do something interesting, which let's put the patient, make him active. So put PMOS. So let's, for example, add a PMOS of like about 5 centimeter water here, and we can change the duration a little bit because here it's only 0.1 second. And of course you can see how the curve, the pressure curve, changed a little bit. So what do you think will happen in volume control? Now the patient will be doing part of the effort. So if you look here, interesting, the ventilator total work really hasn't hasn't changed much, but the patient work is higher, so the total work in the volume control remains the same, and the power is almost the same, because here the PMOS and the PVent contributed to the same, so the in volume control they basically became additive to give the same work. Let's go, it will be a little bit different in pressure control. So again, let's do the same thing here. Compliance of 40, resistance of 10, patient is passive here, respiratory rate is 15, inspiratory time 1 second, I'm sorry. Let's keep the PEEP 5 in this example, and again it will give us the same parameters that we measure here. So and of course you have to look at the tidal volume, 368, because let's try to get it to 400, close to 400, like we were doing with the volume control. So increase the inspiratory pressure a little bit, and the tidal volume now is 405. And again, the shape of the pressure volume curve here is to the right. So if you look here, 10.81, a little bit higher than the volume control. Again, let's worsen the compliance. Let's make it half what if it was 20, and let's keep everything else the same here, because if you notice the inspiratory the mechanical power became less, 5.84. The reason is because when we reduced the compliance but we left the same inspiratory pressure, which is 11/5 PEEP 16, the tidal volume went down to 219, but if you want to keep it the same as about the 400, just to compare the effect here, so we had to go up to 20 of inspiratory pressure, and you can see the mechanical power is now 16.58, which went much higher. The same would happen if we increase the resistance. Let's make it 20, just, and again the mechanical power has increased. Let's put some PMOS again. Let's do it 5 like we did in the volume control. Okay. Now what do you think will happen? The ventilator will give the same work because in pressure control it does not change, but now we have to add the patient work. So if you total ventilator work is here 0.97 or 0.99, the patient work is 0.13, so the total work 1.12, and if you calculate that into joules per minute or power, as you can see, it will be much higher than if the patient was passive. So the mechanical power in passive and active patient will depend on the patient, will depend on the mode used. It does not go the same direction. In volume control, it will be almost the same, but in pressure control, it will increase if the patient became active. We talked about the calculating it from the pressure volume curve, which is going to be very hard really to do clinical, and we talked about the equations that we can be used. But to be honest, patient respiratory mechanics change a lot during mechanical ventilation. What was 40 couple of minutes ago, maybe now 35. Resistance change. Things are very dynamic. Plus, we make changes to the setting on the ventilator. The patient sedation gets increased, so the respiratory rate gets down. We increase the PEEP, and it will be very, very difficult at the bedside. To be honest, not very practical. That every couple of minutes or every couple of hours to go check the mechanical power or calculate it again, because it will be very time consuming. So it will be very nice to have the ventilator do for us the automatic calculation, because it integrates it not from equation but from the pressure volume curve. So this is a picture from Bella Vista, and that's this software is not available in the market yet, or not FDA approved, but we use it for research. And basically the ventilator calculates for us, as you can see, the work, the inspiratory work. Sorry, this is the tidal work, the inspiratory work, and the total work. So for this example, it's 20.2. Patients start breathing harder, become faster. This will change almost breath by breath. Compliance changes, resistance changes, you make changes. It's always in front of us. And I think that's probably the best way to keep an eye always on what's going on with the patient mechanical power. We talked before in another videos about the transpulmonary pressure, and now there is another concept called the transpulmonary mechanical power. Now, unfortunately, there is not many studies about the transpulmonary mechanical power, maybe a few of them, but the idea is to calculate the power according to the transpulmonary pressure, not the whole respiratory system. So if you look in this example here, this figure, and the top here is the airway pressure, and the pink is the flow. This squiggly line, the third one, is the esophageal pressure, and the bottom one is the transpulmonary pressure. So we know that the transpulmonary pressure, the end inspiratory, is the difference between the plateau pressure after an inspiratory pause here, minus the esophageal pressure. So for this example, the airway pressure is 27, the esophageal pressure is 13, so that gives you end inspiratory transpulmonary pressure of 14. This patient is on, I think, PEEP of about 15 or 16. I can't really see very good. Esophageal pressure here was like about 11, so the end expiratory transpulmonary pressure was 4. So instead of the calculation for the regular mechanical power was 0.098 times respiratory rate times tidal volume square multiplied by half the whole respiratory elastance, of course, plus P times tidal volume. Here we're going to use, to calculate the transpulmonary mechanical power, we're going to use the elastance of the lung instead of the elastance of the whole respiratory system. And how do we get the elastance of the lung? Basically, elastance is pressure over volume. Again, difference from the reciprocal of compliance, or 1 over compliance. Compliance will be volume over pressure. So in this example, the elastance will be the transpulmonary driving pressure, which is 14 minus 4 here. So that's 10 over the tidal volume, which is really not, sorry, it's not showing here. For example, if it was 40, which is 0.4, so that will be 10 over 0.4, which is like about 25. So why transpulmonary mechanical power is important? Again, because it eliminates the, this is the, we're using now the transpulmonary driving pressure, which really represent the strain affected on the alveoli. We know strain is related to pressure, or the transpulmonary pressure. Also, there's some studies that show that maybe transpulmonary mechanical power is more meaningful and maybe more related to mortality or lung injury than the whole respiratory system mechanical power. We're doing some other studies and some concept about, as I mentioned here, we're using the whole tidal volume. In all the equations, we're using the whole tidal volume, but especially when it comes to the transpulmonary mechanical power, we know that the alveoli does not see the whole tidal volume that the ventilator gives. There is an area called dead space, which is the anatomical dead space, with the tubing and the airway resistance, sorry, with the airways and the tubing, plus part of the alveoli also does not contribute. So the theory is that we should probably not use the whole tidal volume, but more try to calculate the alveolar tidal volume, because that's the distending volume of the alveoli and might be related to the functional residual capacity. To calculate this, we need both the esophageal balloon to measure the transpulmonary pressure, and we need the volumetric capnometry also to calculate the alveolar tidal volume minus not the whole tidal volume, just remove the anatomical dead space. Here, as I mentioned in the beginning of this talk, about some questions or problems with the mechanical power, and that's why I said we are not there yet. I mean, there's a lot of progress have been made, especially with the concept of mechanical power, but we have so many unanswered questions that needs a lot of research before we really adopt it in everyday clinical practice. I put here some examples. Some of them are mine, some are already been talked in the literature. One is mechanical power and ventilator-induced lung injury. The hypothesis is made that mechanical power is related to the ventilator-induced lung injury, but I think we need more studies, especially on which components of the mechanical power related to the lung injury. How about mechanical power and mortality? Lots of, again, studies showed that it is related to mortality. although some other studies showed there was no correlation with mortality. Um, maybe actually they showed that the transpulmonary mechanical power might be more related. Now, another question which not much talked about in the literature, and I saw conflicting results as usual, is the healthy lung or the injured already lung more vulnerable to lung injury from high mechanical power? There's some concept that the healthy lung is more vulnerable. Another theory is no, maybe the already injured lung is more vulnerable. Again, those are from some animal studies. So we need to clarify this a little bit. The assumption is in a healthy person, healthy respiratory system, say post-operative or neurological problems or airway protection, if the lung is healthy or the whole respiratory system is healthy, you wouldn't need very high mechanical power to ventilate him. As we mentioned before, which one is more important or we should pay more attention? Is it the whole system respiratory mechanical power or the transpulmonary mechanical power? And we talked about the literature. In my mind, I think it's probably more the transpulmonary mechanical power, but again, that's just my own opinion. Another question which was raised maybe in one or two articles, and we did some research about it, is indexing the mechanical power. Now, for example, if somebody has, you're ventilating two patients, both have the same mechanical power of 15, but one with okay compliance, say 60 or 70, and somebody else with a compliance of 30. Are those the same? Probably not. Maybe we should index it or correct the mechanical power to either the compliance or the elastance. Some people said maybe to the tidal volume. Some other people suggested to the aerated area of the lungs, whether by CT scan or EIT. So this is a very interesting concept that again, we worked on it in the bench studies, but needs to be more investigated clinically. I might have touched base on this before about the concept of alveolar compliance and alveolar mechanical power, and we're currently working on a paper to try to discuss it. Again, because we're targeting tidal volume that only goes into the alveoli. Again, we talked about this also before. What component of the power is more important? There's some discussion and disagreement in the literature. For example, is the static PEEP power, is that really, because it's static, is that related to the mechanical power? Some people say yes, some people say no. The reality is PEEP, even if it's static at the end of exhalation, is affecting the functional residual capacity and the compliance of the respiratory system. How about auto PEEP? Very interesting question, and again, there is nothing in the literature to describe this. Most of the equations used assume that there's no auto PEEP, and we're not exactly sure. We wrote a couple of paragraphs about in a recent study that I'm gonna put it in the reference when we studied one of the closed loop ventilation, and we're trying to calculate what the effect of auto PEEP on the whole mechanical power. Now, another question is, should we target certain number of mechanical power or a target? And this really kind of scares me because for years or decades we started targeting certain tidal volume, like the ARDS network, 6 milliliter per kg, thinking if we're doing 6 or below, we're saving lives. If we're doing 7 or whatever, or 8, we might be killing patient. As we talked about, there was some studies here also about mechanical power that if mechanical power above 12 or 15, and mechanical power above a certain number may be related to mortality. But again, I would really caution about this because we don't know exactly, and every patient is different, every respiratory system is different, and that's why maybe again I go back to the indexing. The mechanical power might be better. Of course, we know that the lowest mechanical power is probably better because you're having less energy going from the ventilator to the patient with less risk. But I would really caution about this. I would also caution about that we should think about every single parameter we are adjusting on the ventilator, respiratory rate, not only tidal volume or driving pressure, respiratory rate, flow, PEEP, everything. As we talked before, again, measuring the mechanical power, what is the best way? Is it using calculations or try to interpret the pressure volume curve? Again, what about the passive versus the active patient? And I know some people are already working about this, the effect of the PMOS, and we showed it in that SIVA simulator. We talked about automatic measurements, so probably would be great. And the other question, which is really important, is what is the role of the new closed loop modes in reducing mechanical power? The example I would give is adaptive support ventilation, ASV, and the adaptive ventilation mode, which is AVM. And there is already studies about ASV or IntelliVent and AVM might reduce the mechanical power based on clinicians' set values on the conventional mechanical ventilation. And again, I will put those references at the end of this talk. Those are some references that I really like, and of course there is the literature now is full of articles and discussions about mechanical power. I picked those not in any not in any particular order. This first one with Gattinoni, the initial one about describing mechanical power. This one by Giosa, also Marini and Gattinoni, called Mechanical Power at a Glance, which described the equation, more simplified equation for the volume controlled mode. This one by Becher, which is also described the calculation of mechanical power for the pressure controlled modes. I like this article too by Silva called Power to Mechanical Power to Minimize Ventilator-Induced Lung Injury. This is also a nice study by Coppola about effect of mechanical power and the transpulmonary mechanical power in mortality for ARDS patients. This study by Arnal about airway and transpulmonary driving pressure mechanical power chosen by IntelliVent ASV for mechanically ventilated patients. Also described the mortality of relation to mechanical power and transpulmonary pressure. This is the study, one of the studies that we published in our group, which is examining the mechanical power in AVM2 versus conventional modes, volume control and pressure control modes in various ARDS lung modes. It's a bench study, but that showed that closed loop modes like AVM was able to reduce the mechanical power compared to low tidal volume ventilation. This is also a very nice study by Van der Stey and Shabburn, which they talk about advanced modes of mechanical ventilation with optimal targeting schemes in relation to the mechanical power, which I got some of the figures from it. This is also a great study by Marini. It's not a study, it's just a review or his opinion about the evolving concept of safer ventilation in relation also to mechanical power. And this is a study from China, I think, about individualized mechanical power ventilation strategies for ARDS. I hope this wasn't a very long video, and I hope we included the most important stuff. And hopefully we can do a follow-up one once we have more information about mechanical power and mortality, etc. Thank you very much for your time, and hopefully that was helpful, and we'll see you in other videos. Bye.